Hello and welcome back to the second part of chapter waveform generators. Myself Sanjit Kumar Singh, lecturer in Electronics and Telecommunication Department at Praveen Patil College of Diploma Engineering and Technology. So in this presentation we'll cover up the crystal oscillator concept, working and applications. Then sweep generator, the Miller sweep generator will be covered in this presentation. So what is crystal oscillator, how it looks like, the circuit diagram and the frequency of oscillation, advantage, disadvantage and application we'll see. So crystal oscillator, basically it is a tuned oscillator. The crystal oscillator makes use of piezoelectric crystal as a resonant tank circuit. The crystal is usually made of quartz material and that can provide a high degree of frequency, stability and accuracy. Therefore, crystal oscillators are very useful in these applications where the frequency stability is of importance. The crystal oscillators are widely used in communication transmitters, digital watches and clocks. So quartz crystal have a very peculiar property, that is piezoelectric effect. What is this effect? When an AC signal is applied across a quartz, it vibrates at a frequency of the applied voltage and vice versa. So the material that could be rock salt or tourmaline also exhibit this piezoelectric effect and can be used in place of crystal oscillator. So quartz crystals are available with constant frequencies ranging from 15 kilohertz to 10 megahertz. So that is the higher frequency ranges, and even for higher frequencies up to 100 megahertz, the crystals can be made to vibrate on overtones. So when the crystal mounted across the AC source is not vibrating, then its equivalent circuit is equal to the capacitor C2, as we can see in the diagram of equivalent circuit, the second diagram below. When it vibrates, it acts like a tuned circuit, series resonant tuned circuit, RLC1. So the two arms, RLC1 series arm and the parallel arm consisting of C2 when the source is not vibrating. So series resonance occurs, we know, when the inductive reactance is equal to capacitive reactance and the overall equivalent impedance of the circuit, tuned circuit, becomes equal to resistance value R. In that case, the series resonance Fs is equal to given as 1 by 2 pi root over L into C equivalent, where the C equivalent will be C1 into C2 by C1 plus C2, and parallel resonance similarly is obtained when the reactance of the series arm, that is RLC1 branch, is equal to the capacitive reactance of the second arms consisting of C2. So for the parallel resonance also, the frequency of oscillation is 1 divided by 2 pi multiplied with root over L into C equivalent, where C equivalent again the same product by the sum of the two capacitances. But C2, since C2 value is far greater than C1, therefore the equivalent capacitance will be nearly equal to C1, and therefore series resonance is equal to parallel resonance. So crystal oscillator, the Q factor is of importance, and for tuned circuit it could be as high as 20,000, that is nearly 200 times more than that of LC tank circuit based Q factor, and therefore it provides a stable frequency output. A variety of crystal oscillator circuit is possible, like the twin collector oscillator, Colpite crystal oscillator, clap crystal oscillator, etc. But pairs crystal oscillator is most commonly used. In pairs transistor pairs oscillator, it consists of series element in the feedback path from the collector to base. So we see a capacitor also connected in series with the crystal. So R1 and R2 and R3, these are the resistors that provide biasing and divider, voltage divider, stabilizing the DC bias circuit. The bypass capacitor CE, that allows only the AC signal to pass through, and the radio frequency choke coil provides for DC bias circuit while decoupling any AC signal on the power lines from affecting the output signal. The capacitor C connected between base and collector is the coupling capacitor and has a negligible impedance at the circuit operating frequency, but it blocks any DC between a collector and base. So the overall frequency of oscillation of a crystal oscillator is equal to the series resonance, that is equal to 1 divided by 2 pi root over LC1. C equivalent is equal to here C1. Secondly, we can implement the crystal oscillator using FET as well, rather than making use of a transistor BJT. The circuit arrangement is shown in the adjacent figure. The crystal is connected between the input and the output of FET. When DC voltage is applied, crystal vibrates with applied voltage frequency. That frequency signal is fed back to FET, and we get continuous oscillations having high frequency. FET version provides a higher input resistance to the crystal. Frequency of oscillation is same as the BJT based pairs crystal oscillator, that is frequency of oscillation FO is equal to series resonance frequency, that is equal to 1 divided by 2 pi root over LC1. So now what are the advantages of crystal oscillators? So high frequency stability is its major advantage with the quality factor value of 20,000, and therefore it has very low frequency drift due to voltage supply or transistor device parameters. The major drawbacks include its mostly it is used for frequency of 15 to 100 kilohertz or even 100 megahertz with a special modification can be used. So that is a higher frequency application. Crystals of low fundamental frequencies are not easily available. Applications: crystal oscillator has many applications based in the basic timing device like digital watches. It can be used in clock, as a clock, in microprocessors and microcontroller, in frequency synthesizers, in radio and TV transmitters, medical devices, electronic countermeasures, and cellular phones. So here is a simple numerical where some of the parameters are given, and we have been asked to calculate the series resonant frequency and the quality factor of the crystal. So here in this numerical, inductance L value is given as 0.33 Henry and capacitance is given as 0.065 picofarad with C2. When the crystal is not resonating, that capacitance is equal to 1 picofarad and resistance of the crystal is 5.5 kilo ohm. So with these values we know the series resonant frequency is Fs is equal to 1 upon 2 pi root over L into C1. Therefore substituting the corresponding value of L and C1 into the formula, we get 1.09 megahertz, whereas the quality factor of the crystal is calculated as 2 pi Fs L by R. So by substituting the value of Fs just calculated above, 1.09 megahertz, and the L value as 0.33 and R value as 5.5 kilo ohm, we get 411 as the quality factor. And here is a second numerical in which we have been given again the inductance value 2 Henry, capacitor value is equal to 0.01 picofarad and resistance 2 kilo ohm, and the mounting capacitance is 2 picofarad. So mounting capacitance is nothing but the C2 value, and we have been asked to calculate the series and parallel resonance frequency. So Fs is equal to 1 upon 2 pi root over LC, and substituting the value of L as 0.01, L value as 2 and C value as 0.01 into 10 raised to minus 12, we get the series resonant frequency as 1.125 megahertz, and the equivalent capacitance of the two capacitance C value 0.01 picofarad and the mounting capacitance as 2 picofarad will be the product of the two, C1 into C2 by C1 plus C2. So we get 9.95 into 10 raised to minus 15 farad. So now in order to calculate the parallel resonance frequency, the formula again is same, but here 1 upon 2 pi root over LC equivalent. So C capacitance equivalent we just calculated as 9.95 into 10 raised to minus 15, that value is substituted, and L value is 2 Henry. So substituting that value we get the parallel resonance frequency as 1.128 megahertz. Next we have the time-based circuit. Time-based circuit, there are different methods of generating time-based circuit. A time-based circuit is where the output voltage or current is linearly proportional to time. There are different methods of time-based waveform generation. The four important are given here. Exponential charging method. So in this method, a capacitor is charged through a resistor to a voltage which is smaller than the supply voltage. So if the supply voltage is 10 volt, the capacitor will charge up to 9 point something, so it will not charge up to exactly 10 volt. So that is exponential charging. The adjacent figure shows that exponential charging, where V is the supply voltage and RC is the circuit where capacitor is charged when supply voltage is turned on, and output voltage is taken across the capacitor, and when when a switch is connected across the capacitor and is closed, then the capacitor discharges. So that switch can be electronic switch or it could be manual switch. Second method is constant current charging. A capacitor, in this method a capacitor is charged linearly from a constant current source. So a constant current charging method involves constant current source, whereas third method is Miller integration, where an op-amp or BJT transistor based integrator is used to convert a step input, a step input into a ramp waveform. And the fourth one is bootstrap, where a constant current is approximated by maintaining nearly constant voltage across a fixed resistor in series with a capacitor. So let's see the Miller sweep circuit as our syllabus given. So Miller sweep circuit is also called Miller integrators. In the circuit arrangement, we are seeing two transistors, transistor Q1 and transistor Q2, where the first transistor Q1 acts as a switch and the second transistor is acting as a high gain common emitter amplifier. And we are assuming a condition where Q1 is in on state and Q2 is in off state initially. At this condition, the voltage across the capacitor C and the output voltage V out is equal to VCC. When a negative pulse is applied to the base of Q1, that is at Vi, then the emitter base junction of Q1 is reverse biased and hence the first transistor Q1 is turned off. Thus the collector voltage Vc1 of the Q1 transistor increases, which increases the bias to the second transistor Q2, and as a result second transistor is turned on. Since now Q2 is conducting, V output voltage begins to decrease. Because the capacitor is coupled to the base of the transistor Q2, the rate of decrease of the output voltage is controlled by a rate of discharge of capacitor, and the time constant of the discharge is given by T discharge is equal to RB2 into C. This is the RC time constant, RB2 into the capacitor C. So as the value of the time constant is very large, the discharge current practically remains constant, hence the rundown of the collector voltage is linear. When the input pulse is removed, when the negative pulse from the first transistor base is removed, then the Q1 turns on and Q2 turns off. The capacitor charges quickly to VCC through RC with the time constant T is equal to RC into C. Here RC is the collector resistance of second transistor and C the capacitor connected between collector and base. So sometimes this RC will be replaced with a diode, so that the diode's small forward resistance will help the capacitor to charge quickly from the VCC supply. This reduces the flyback or the TR time in the waveform, and therefore it will have a generated a sweep circuit. The Miller sweep generator is excellent sweep linearity is there. So thank you, that's it.